Okay, yes, I'm Ben Kent, currently at CNR-IMATI in Pavia, and I'm going to talk about some work I've been doing with Lorenzo Tamolini on multi-fidelity surrogate modeling, and in particularly how we're using Umbridge to speed up our development process for this. So thanks again for the organisers for letting us share our work. Hopefully this is going to be interesting for all of you. So I'm going to start by motivating why we need to do multi-fidelity modeling with this NASA 2D wall-mounted hump test problem that we've been using. So this was originally designed by NASA in 2004 as a validation case for turbulence modeling, and we're using it as our test problem in our surrogate modeling. So once I've motivated why we need to do multi-fidelity approximation, I'll explain a little bit how we do it, particularly using the multi-index stochastic collocation algorithm. And after introducing the algorithms, I'll explain how we've used Umbridge to move from simple analytic test problems and developing our algorithm to now solving these complicated problems on an HPC type setup. So I'll just conclude with some of these advantages, but also some of these challenges that we are still facing even in this setup. So we're talking about surrogate modeling, we're talking about taking a parameterized problem and producing some sort of response for the quantity of interest. So in my talk, I'm going to call these parameterized inputs y, and they'll sit in some sort of parameter domain gamma, and then they'll map through to some quantity of interest, which I'll generally call q, and for the purposes of this talk, will just be a real number. So in our surrogate modeling, we're considering this NASA 2D wall-mounted hump system. And it's pretty self-explanatory. So in practice, it's a two-dimensional problem. So they had two very close plates put together. We have this bottom wall along here with a wall-mounted hump. And then we have a fluid flow from the left, which is going to be steady and laminar and of magnitude capital U. It flows over the hump, and then we get some turbulent effects behind the hump. So we're going to do some surrogate modeling to compute some quantities of interest on this flow. So then the other thing we need to know is also in this setup, there's a little suction jet just at the back of the hump, which can be used to control the fluid flow. So in surrogate modeling, we can describe these with our parameterized inputs, and we'll do form some sort of surrogate model, allowing us to evaluate our quantity of interest for all possible points in our parameter domain. So more specifically, in our setup, we were looking for the flow reattachment point behind the hump as our quantity of interest q, and we've got these parameters which sit between 0 and 1, and they simply just control our outflow jet speed and our inflow speed. So in the original experiments, they used these values of 23.4 and 34.6, and in our numerical experiments and in our parametric model, we've just got these as affine functions, so going from about 10% to 100% of these values. So in practice, we have this flow over the hump, we get this recirculation, which is controlled a bit as well by the sucking of this jet outwards, and we're interested in this reattachment point where the flow rejoins the wall and goes forwards. So we can solve this, we get fluid flows, we get the flow fields, and we get the pressure fields, and we do some post-processing on the skin friction to tell us where this reattachment's occurring. So here on this figure, it's where the 0 is, because there's no friction, is where it's reattaching, and it's about 1.1. So obviously we can't do lots and lots of experiments. We look to numerical solvers, and people have been studying these things for many years, but particularly for single realizations, obviously. So we can use these non-intrusive methods where we can use the existing solvers for different realizations of our parameters to compute the reattachment point q for different choices of our parameter y. So that's kind of the fundamentals of surrogate modeling. And in particular, we're going to use a Reynolds average Navier-Stokes model with a Spalart-Alvarez turbulence model and solve these equations using the simple foam solver in OpenFOAM, so it's a finite volume solver. This almost tells us enough to get some numerical results. But the final thing we need to do to solve this problem, to approximate the solution for each of our choice parameter y, is we need to choose a spatial mesh and some solver tolerances that go within the simple foam iterative solvers. So people have been studying this, we know exactly how we should mesh it, we know how fine the mesh needs to be near the boundaries to capture the physical behavior of the solution. And in practice, this requires a mesh with 200,000 points and this tolerance of 10 to the minus 10 to get an accurate answer. The problem we have is that if we solve this once on our moderately powerful computer, it takes about 3 hours. If we're forming a surrogate model and need 10, 100 realizations of our parameter y, this is very expensive. We don't really want to be spending 2 weeks to form our surrogate. So what can we do? Well, the first thing we could do is we could just use a coarser mesh and a coarser tolerance. So we could use a much coarser mesh with only 35,000 points and a much coarser tolerance in our iterative solvers. And this is nice. We now have an approximation in about a minute. The problem is, so if we can do this, we can then form a surrogate very easily. We can solve it 10, 100, 1,000 times without worrying too much. The problem is we've thrown away all the knowledge about the modeling that we put into forming this mesh in the first place, and we kind of expect this to give us garbage. But is there anything we can use this low fidelity model for? Can we extract some information and then supplement it with a few high fidelity solves to give us a multi-fidelity approximation, which is almost going to be as accurate as our high fidelity solves? So we can form surrogates using our low fidelity model and our high fidelity model, and to do this we use sparse grid interpolation to form global polynomial interpolants over our parameter domain. And in the eyeball norm, if we look at these two plots, the low fidelity surrogate captures with the right sort of shape some of the behavior as the same as the high fidelity surrogate at 2 orders of magnitude less cost. So there is something useful we can get out of this. If we look at the error surfaces, of course, the low fidelity surrogate isn't that accurate. But what we want to do is we want to try and take this low fidelity one, correct it to get closer to this high fidelity, and hopefully attain something which is of similar, well, approaching the same approximation quality. So in practice, how do we do this? Well, this is a cartoon sketch of how we form our multi-fidelity approximation. So we have our quantity of interest Q, what we're trying to form a surrogate model for, our function we're forming a surrogate model for. And we're sort of expecting that our high fidelity model, if we can do many solves, that we're going to achieve something which is similar, relatively accurate. We know this isn't attainable. We can't reach this box, it's too expensive. But we can get these other 3 boxes. We can use a low fidelity solver with many solves, we can use a high fidelity solver with a few solves, and of course the low fidelity with very few solves. And what we want to do is we want to try and piece these together in a way that gives us something which approaches this high fidelity approximation with many solves. So we can start in this bottom corner, and then we can look at what happens if we make this correction to move to this high fidelity with a few solves, this difference here. And similarly, we can look at what happens if we make this correction to go from the bottom left to the top left and add that on. And in a hand wavy sort of way, as we could imagine the 2 vectors adding together to giving us something in this top right corner. And then we simply have our surrogate is just going to be a linear combination of different surrogate models formed in different ways using different combinations of high fidelity models and high fidelity parametric approximations. So this is exactly what happens in practice if we use our multi-index stochastic collocation algorithm. So here we could imagine having 4 different fidelity models, fidelity 1, 2, 3, and 4. Fidelity 1 being the cheapest, we can solve this many, many times. And we use these things called sparse grids to form our approximations, which gives us this strange shape to our approximation space. To our sampling space. Fidelity 2, a little bit more expensive, we can do slightly fewer solves. Fidelity 3, again more expensive, we're going to do 5 solves, and Fidelity 4 we do a single solve because it's very expensive. What the multi-index stochastic collocation algorithm does, it tells us how we can piece together these different approximations to give us a sensible approximation for our quantity of interest. So we have these different fidelity models, Q alpha, different levels of interpolation, defining these different grids that we're going to interpolate on. And then it's just a linear combination with these coefficients C, which depend on these what I'll call multi-indices, the things which are controlling the fidelities in our different approximations. And of course, we don't want to just define this a priori. The now standard way of doing stochastic collocation or multi-index stochastic collocation is that we use a greedy algorithm that can select the best fidelity and parametric accuracy combinations, and we progressively build up our approximation like so. So there's more details in this paper by Chiara Piazzola and Lorenzo Tamolini with an extremely long title, which is on the slide two slides in. So what happens if we apply this algorithm to our 2D wall-mounted hump test problem, where we're looking for this reattachment point? So we apply it, and we're allowing our total computational cost to grow as we go through the algorithm. So we're adding more and more points. So we start off, it's very cheap to form the approximation. We're limiting the computational cost, and our MISC algorithm selects to use these low fidelity approximations. And we see that we're able to start capturing the behavior, and the approximation error goes down. We then have this big jump as we then have to add a high fidelity approximation, and this pushes the approximation error down further, but it's obviously much more expensive. And then we kind of stagnate a bit, and we get a little bit of improvement as the algorithm is allowed to add more and more points and through more and more cost, until we see that actually we're just catching up with the approximation, a surrogate approximation using just the high fidelity model. In the end, obviously, the low fidelity is not providing more information than the high fidelity approximation, so we do just sort of converge to the high fidelity approximation. So what we're really seeing is these MISC algorithms and these multi-fidelity algorithms are really going to be advantageous when we've got limited computational cost, or if we only want a moderate level of approximation accuracy. But in these circumstances, they are pretty powerful. So this was kind of just an overview of multi-index stochastic collocation and multi-fidelity approximation. So if you're interested in the surrogate modeling side of things, then the first starting point is the sparse grids in a single fidelity. So I suggest perhaps looking at this user manual type paper, but all the code for this is available online, and as you'll see in the second half of this talk, interfaces very nicely with the Umbridge toolkit. There is, of course, this multi-index stochastic collocation I just talked about, and this is detailed in this paper with the longer title that I cut short on the previous slide, but the code isn't yet released yet. We're planning to release it very soon. The reason we haven't released it is because we're working on this more complicated test case and some modifications to the algorithm, a novel addition to the algorithm, I suppose. But again, we hope to release this soon, and this will also be compatible with Umbridge, because that's how we're really working to speed up our development of this code. So that was just an introduction to the multi-fidelity side of things. Next, I'm going to talk about this connection through Umbridge. And this is a sentence, I think, either from the workshop website or the Umbridge website. It's speeding up UQ projects from prototype to HPC, which is exactly how we've managed to use it in our setup. So of course, when you're doing algorithm development, you don't start with a complicated turbulent flow problem. We do our development perhaps on an analytic function, something like this two-dimensional Gaussian. So this is from the suite of Gens functions, which are often used as benchmark test problems for interpolation and quadrature algorithms. And we can do this because it's easy to write, it's easy to solve, it's very quick to use. And also for the exposition of our algorithms, we know things about the analyticity of the function with respect to the parameters, etc. And we can start to prove things and argue why we're doing things in our algorithmic setup. That, of course, isn't very practical. So often the next step is we move to something like an elliptic PDE or a parabolic PDE if we're feeling adventurous in numerical analysis. And These are still relatively simple. We still know lots of things about the properties of the problem, where they're analytic in the parameters, and we can talk about convergence rates and stuff. But we don't necessarily want to use these bits of code in the same language that we're using to do our algorithm development. So the sparse grid stuff we're working on is all in MATLAB. Perhaps we'll write our solves in MATLAB, but we also want to be able to connect it through and test this on and use other packages to develop our PDE problems that are perhaps slightly more optimized, so like this PETSI library or the Phoenix project to define our problems. So this is nice. This gets us something which is practical and can show off our algorithms. But of course, the real step is to move to more real-world examples. So, for example, turbulent flow over aerofoils, which again is a sort of step up again from what we're looking in this 2D wall-mounted hump problem. But here we know a lot less about the mathematics. We probably can't prove that it's going to be analytic with respect to our parameters when we're doing our analysis. But it shows we often have nice properties still, and we can really demonstrate worth in our algorithms. So here we might be connecting to something like our OpenFOAM solver, or we might be wanting to connect to some engineering Fortran code that people have been working on for many years, and can show off our algorithm on something which is much more meaningful. And these things are often much more computationally expensive. I can obviously solve the analytic function on my laptop, these MATLAB functions, these PDEs solvers probably on my laptop. But we start moving to the realm where we have to start using HPC systems to start solving our problems, particularly when we want to scale up to many, many solves. And this, of course, is where the beauty of Umbridge really is. So when we're doing our algorithm development, we want to be able to use a common interface for all of our problems. We want to evaluate our function, our quantity of interest, or Q or U, so U here now, sorry, at different fidelities alpha, for many sample points Z in our parameter space. And we want to be able to do this in exactly the same way for all our models. And this is where the Umbridge interface allows us to do that. We want to be able to work locally. I want to be able to develop my algorithm on my laptop. But I want to be able to use my server in Pavia to do my solves, or an HPC system somewhere to do my solves, which are unattainable really on a laptop. And one of the nice things about our sparse grid setup is we're often introducing many points at once, so we can parallelize our solves. So we want to be able to do this as well in an easy way that our algorithm on the left doesn't have to see, but doesn't particularly have to see. And we can scale it up very easily. So this is exactly what we can do with Umbridge. So we design our algorithm, we test our algorithm initially with a simple one line of code analytic function. So this is just our gens function, our Gaussian, two-dimensional Gaussian function. So we just give it a parameter and we give it some fidelity level. So we're just adding some noise, some artificial noise, and we can do our development very easily. Once we've developed our PDE models, we can just wrap these up in an Umbridge server type thing, and then we can deploy these locally. And to MATLAB, to our algorithm, we simply we create this model using the Umbridge code. And then to our algorithm, we simply see exactly the same interface. We take a parameter y, we take a fidelity alpha, and it just feeds into the model, and everything else is handled behind the scenes in our server. So this is great for development because we can then just develop one single piece of code. We don't have to worry about interfacing with many different types of software or importing pre-computed values from CSV files and stuff, which we were doing in the past. We now have this universal interface, and this is the same for our RAND solver as well. We don't have to worry about anything else. It's exactly the same. We just feed in our parameters and our fidelities. So this is nice, but we said we don't want to be running all of these models on our laptop. We want to be able to run these models externally. So the next step we took, and this is kind of following the development of many of the Umbridge examples, is we packaged up our approximations, our solvers into Docker containers, and then we can run our Docker containers externally on our computational server. And then once we've done this, we can query it remotely. So I can be working here in Milan whilst the server's in Pavia, or I could be, well, Lorenzo's in Barcelona, he can query it as well. I could be back in the UK, and we can do all our work remotely while still having our solvers running on a much more powerful system. And I'm sure we'll hear more about this tomorrow. Packaging it up in a Docker container is relatively straightforward. You just choose your environment, install your dependencies, and then run your server. So this is all well and good, but I talked about parallelization. We don't just want to be running our 3-hour solver serially 10 times. When we can parallelize, we want to run it in parallel. So after some discussion with Linus, we were trying to work out the best HPC setup to go for, and we've settled on this Kubernetes setup. And what this does is you just put this block between your Umbrage connection and your model, and this sets up an ingress control, which is load balancing, and you simply tell it where to find your Docker container containing your model, and then it will spin up as many pods, as they call it, realizations of your model as possible, and then you simply just run your algorithm on the left-hand side. We change a for loop to a par for loop, send our queries through Umbrage to this Kubernetes setup, and now instantly, without changing anything on the left-hand side, we have access to many, many instances of our solver, which is really powerful. It's obviously in parallel, we can really speed things up. So I also talked about the fact that we go through this series of developments. We go through our stages of development. So we've got the analytic, we've got the PDE, we've got this OpenFlow model, and we want to be able to run all of these in parallel on our server. And with a little bit more fiddling within the ingress controller of Kubernetes, we've set it up so there's a filter that allows you to append something to the end of your server and port that you're connecting through. And this lets us access our different models that are all running simultaneously on the server. So we've just got one server with one access, and we can run our models. People in Rome can run their models, which is I think a roll-on, roll-off ship piece of ferry model written in Fortran, and everyone can access their models on this HPC system with relatively little expert knowledge in terms of setting it up. And of course, once this is all set up, we're not just restricted to developing our algorithms on our laptops, so we can use all the different Umbrage type setups that are provided online. And we can develop anything else we want to connect to our models. So this week I was trying to produce some figures to share with our collaborators in Barcelona, and our MATLAB license server somehow crashed, and I needed to produce these figures quickly. So I just took the Julia client, and within about half an hour I had the figures produced using these same models, because it was all set up and it's all just got this one shared interface that we can use. So this, of course, is very useful, and that means we can then do our analysis, we can do our development, and produce all our figures using just this shared code, because it's just one single interface. No matter whether we're looking at an analytic problem, our parabolic PDE problem, or even our much more complicated OpenFlow model. So what we're seeing here is that we can just produce all these models, and hopefully when we're applying our multi-fidelity algorithm properly, we're going to get some sort of convergence of the error as we increase computational cost varying on the model. So to quickly conclude, I've just got these same advantages listed again, but I'll highlight a couple of other things. So I talked about the fact that we can now locally develop our algorithms whilst running all our models externally. We can also locally develop our models, despite the fact that they're running externally in this setup. So it doesn't take much to set it up. We can develop our models, we push them to our GitHub, our repository, and through the magic of continuous integration, we can then automatically package it up as a Docker container, which automatically uploads it online. And then through a single line of code on our server, we can automatically roll out this updated model build to all our pods, all our Kubernetes pods, and it's instantly updated our HPC to use our new updated model. So I think hopefully I've really highlighted how we've managed to speed up the development of our algorithm from our prototype to HPC in a very universal way. I will say we are still struggling with a couple of things, and this is through no fault of Umbridge. We're still trying to think about these things, so people maybe have some useful suggestions for us. For us, when we're tweaking our algorithm, we obviously have to repeatedly rerun our tests, and this means repeatedly rerunning our solves. So if we've got a 3-hour solve, we don't want to be repeatedly doing this. We want to save out the data and just be able to call it back in as and when is necessary. And we can do this in the Kubernetes setup through setting up a persistent volume, which is all documented in the Umbridge literature. But the difficulty we have is trying to work out quite how much data to save. Obviously, we could save out the full field data, but a back of the envelope calculation tells us that means saving out terabytes of data, which perhaps our admins will be less happy about. We could save out a post-process set of data. So in this 2D wall-mounted hump system, we could just save out the pressure field at on this bottom wall, talking about a megabyte of data. Or if you really know what you're doing, you could just save out the single quantity of interest. So we're trying to work out exactly where on this scale is best to sit. I think we haven't quite got it right yet, but something we're trying to think about. And of course, there are many other HPC architectures. So we've got access to a Slurm workload type manager hidden behind some layers of login nodes. It may be simple to use and straightforward to access, but we haven't quite managed to work that out yet. But it's more powerful than the server we have at the moment, so it would be nice to be able to use that. So thank you very much. If anyone's got any questions, I'll happily take them, either on multi-fidelity modeling or how we're using Umbridge in our development toolchain. So thank you very much.